Hello, everybody. This is Skip Elsheimer. Welcome to the AV Geeks Lunchtime Streaming Show, where I got caught up on another computer and lost track of time, so I didn't get a chance to get this stream started just a little bit before 1 o'clock like I normally do. Let's watch this film where I look at it and I'm like, is that Mr. Wizard? It totally looks like Mr. Wizard. It's similar to Mr. Wizard, but it's not. Enjoy.
The purpose of this film is to explain what matter is, to define three kinds of matter, solids, liquids, and gases, to introduce us to molecules, atoms, and elements, and to show the difference between mixtures and compounds. Mark's hobby is building things. Dad's hobby is taking pictures.
Dad, why does a burned-out flash bulb look cloudy?
Well, let's open it up and find out. Now, a new flash bulb is filled with thin metal wire. See? And when the bulb flashes, that wire is changed into a powder. And most of the powder sticks to the inside of the bulb. And that's what makes the glass look cloudy.
But, Dad, how could the wire change into powder?
Well, that's a good question. Let's see, how can I explain it? You see, both the wire and the powder are kinds of matter. Do you know what matter is?
I think so.
Well, to understand how the wire changed into powder, we need to know what matter is. Now, actually, everything around us is called matter. Clouds in the sky, the trees, and the flowers, the ground we walk on, the house we live in, the furniture in the house, the water we drink, the air we breathe, our clothes, even our bodies. Anything that takes up space and has weight is called matter. Now, there are three main kinds of matter. One kind of matter is called solids. This knife, the metal wire in the glass bulb, the glass, the powder, and the handkerchief are all solids. Now, solids have a definite size and shape. When we put the knife in the bowl, knife keeps the same shape. Now, liquids are another kind of matter. For instance, water is a liquid. Liquids have a definite size, just as solids do. But watch. Liquids do not have a definite shape. They take the shape of the glass or whatever we put them in. The third kind of matter we call gases. The air all around us is a gas. Now, you can't see gases, but sometimes you can smell them. For instance, the odor from an onion is a gas. When we cut an onion, it doesn't take long for that odor to reach our nose or our eyes. You see, gases have no definite size or shape. Whenever a gas is put into a container, the gas spreads out, taking the size and shape of the container. Now, since everything is made of matter, let's try to find out what matter is made of. For instance, let's take a sugar cube and see what it's made of. Now, when we crush the cube, we find that it's made up of many small particles of sugar. When the particles of sugar are ground up very fine, we have powdered sugar. Now we have particles of sugar that are much smaller than before. And if we look at these tiny particles through a magnifying glass or a microscope, we find that they're made up of still tinier particles. If we could keep on breaking the sugar into still smaller and smaller particles, we would finally have the very smallest particles we could get that would still be sugar. These particles are called molecules. Molecules are so very tiny that we can't see them, not even through an ordinary microscope. A single grain of sugar is made up of trillions of molecules. And a molecule, remember, is the smallest particle of sugar we can get that is still sugar. But as small as molecules are, they're made up of particles still smaller, called atoms. Materials that are made of only one kind of atoms are called elements. Now, some elements we see and handle every day. Copper, nickel, silver, gold, and iron. In all, there are 92 different kinds of elements found on the Earth, and scientists have made at least 11 others. Now, elements are sometimes called the building blocks of matter. You know how sometimes you can take a set of building blocks and put them together in all sorts of different ways to make all sorts of different things? We ourselves can take different materials and sometimes form new materials. Let's try it. With some sugar and sand. Now let's pour the same amounts of sand and sugar. You take the sugar, Mark. Pour it into the bowl. Now, sand is different from sugar because sand molecules and sugar molecules are made up of atoms of different elements. That's about it. Now, you take this spoon, Mark, and you stir it up together. When we stir the sugar and sand together, we don't form a new material. All we have is a mixture of the two materials. When we form a mixture, we can easily separate the two materials from each other. To separate the sand and the sugar, we pour water into the mixture and stir it up. The water dissolves the sugar. After a while, the sand will settle in the bottom. Now we can pour the water off into another container where the water will evaporate. And we spread out the sand to dry. Well, now after all the water is evaporated, what do we have?
Here we have sand.
Mm-hmm. Same sand we started with. And how about in this bowl?
Sugar.
That's right. So we started with a mixture, but now we've separated that mixture into sugar and sand, the same materials with which we started. Now let's try combining baking soda and vinegar. You can see that something is happening. We're forming a new material. We've taken a solid, baking soda, and a liquid, vinegar, and formed a gas called carbon dioxide. We can't see the carbon dioxide gas, but we can pour it out of the jar. When we pour it over a candle, it puts out the flame. Whenever we form a new material that looks and acts differently than the materials we started with, we call that new material a compound. And now, Mark, I'm ready to answer your question. The powder we found in the used flashbulb is called a compound. How was it formed? Well, to start with, a new flashbulb contains metal wire and a gas which we can't see called oxygen. When we take a picture, we send electricity through the bulb to make it flash. The heat produced makes the metal combine with the oxygen to form a new material. The new material is the powder which sticks to the inside of the glass. Now, this powder looks and acts differently than either the metal wire or the oxygen, so we call it a compound. And that's why a burned-out flashbulb looks cloudy.
Now let's review what we have learned. Everything around us is made up of matter. Matter is anything that takes up space and has weight. There are three main kinds of matter: solids, liquids, and gases. Solids have a definite size and shape. Liquids, such as water, have a definite size, but they take the shape of whatever we put them in. Gases, such as air, have no definite size or shape. When a gas is put into a container, the gas spreads out, taking the size and shape of the container. Molecules are the smallest particles of any material that are still that same material. Molecules are made up of even smaller particles called atoms. Materials that are made of only one kind of atoms are called elements. Elements are like building blocks of matter. They can be put together in all sorts of different ways to make hundreds of thousands of different things. Sometimes when we put two materials together, we get a new material. We call this new material a compound. A compound looks and acts differently from any of the materials it's made of. Sometimes when we put two materials together, we don't get a new material. All we get is a mixture of the same materials with which we started. Mark left this trowel in the garden for several days. It's rusty. Now, rust is a kind of matter, isn't it? But why is there rust on the trowel? And what is rust made of? Do you know the answer?
So I've seen that guy's face before, and he certainly narrates a bunch of educational films. Yeah, because the format of it, I was like, man, this feels like this is a Mr. Wizard, but it is definitely not. I compared photos, and it was definitely not Don Herbert. The way he talks is different, all that stuff. So there you go. All right. This is Mission to Earth Part 2, Life Forms and Resources, and I feel like we've shown another Mission to Earth, and this is a really weird thing, because it's trying to explain ecology and, just life on Earth and all that, but it's doing it through the context of astronauts, like, flying over the Earth, and it's an interesting take on it. But it does grate on me after a while. I'm like, all right, I get it. I get the point. All right, enjoy.
Orbit stabilized. Probe status.
Probe check complete.
Sensor readout.
Sensor checkout nominal.
Probe launch sequence to automatic. 3, 2, 1. Launch.
Probe to descent mode.
Sensor shield in place.
Time to surface 409.
Color separation to automatic. 3, 2, 1. Jettison.
Sensor shields removed. Life sensor readout nominal.
Time to surface 057.
Secure from launch stations. Command to crew. Probe launch complete. We are now beginning the second phase of our exploration. During phase 1, we investigated the physical nature of the planet. During that investigation, we detected large areas of diversified life forms. The purpose of phase 2 is to investigate these life forms, as well as the resources of the planet as they are used by the life forms. Science section will review our findings to date.
Science section to all crew. We have found a very active planet, number 3 of a 9-planet system. It receives solar energy from its star sun. Atmosphere consists of nitrogen, oxygen, and carbon dioxide. The compound water is found in abundant supply, covering 70% of the surface area. Because of the planet's rotation and the energy received from the sun, temperatures on the surface cause the water to be constantly changing from one form to another. This cycle of water has eroded and redistributed parts of the landmass, but internal forces from within the planet are constantly pushing up new landforms. The water cycle tends to balance temperatures, and all of these conditions have made this planet well suited for life. The surface is dominated by water.
This is infrared scanner image.
Affirmative. Infrared scanner makes plant forms much more visible. These are not true colors.
The large areas of red indicate extensive plant communities.
Sensor position.
Saltwater marsh near coast.
This area is the most biologically productive. The greatest variety and numbers of plants occur in areas like this, where water is abundant, soil is rich in nutrients, and temperature range is mild. The plants we see here are adapted to these conditions, and when they occur, the plants thrive. Notice that as the probe moves inland to drier areas, the plant life becomes less concentrated. Life forms here are much different, adapted to different conditions. Notice that the plants we saw in the marsh do not exist here. They could not survive under these conditions.
In other words, plant communities develop in response to specific conditions of the environment.
Confirmed. On scanners is a different plant community. Broadleaf tree forms. Deciduous trees.
Different soil, water, and temperature conditions allow this form to dominate here.
Another form of tree. Conifers. They dominate here because conditions are again different. They have adapted to the conditions that exist on this part of the planet, and they tend to exclude other, less well-adapted plants.
The dynamic nature of the planet, especially the water cycle, is responsible for these variations.
Here is an analysis of the plant form system. They are the only life on the planet that uses the energy of the sun directly. They convert that solar energy into chemical energy in their green leaves, where carbon dioxide, water, nutrients are converted to a sugar, glucose, which serves as a food for the plant and other life forms which consume the plant. It is a basic system, and on these plants, all other life systems will have to be based.
Even after the death of the plant, the chemical energy is still available for other living things.
Probe positioned for life form scan.
A great many life forms seem to be involved in the system, and we recorded some diverse examples.
They are actually interdependent because the relationship is favorable for all the elements of the natural system. They are all actually dependent on each other. Probe is now at an area of water scarcity and temperature extremes. Plants have adapted to this situation with smaller, thicker leaves which conserve and store water.
What doesn't show on the scanner is the root systems which most plants have. They support the plant physically, as well as extracting water and nutrients from the soil.
Soil analysis data.
Soil varies by area. Composition is of small bits of eroded material and the remains of former life forms. It is another cyclic system. New life forms growing from the remains of the old life forms. Probe approaching higher elevation. Large trees, well adapted to the severe environment.
Large areas of these trees appear to have been removed. Analysis, science.
They have obviously been removed, which means that they are considered valuable by a higher form of life. If they have been harvested for use by these beings, they would become a resource. I suspect we will find extensive evidence of resource utilization as the mission proceeds.
Define the term resource.
A resource is anything which is used, like these trees. But it could be water, gases in the atmosphere, minerals in the soil, or anything else.
The pattern of these rock deposits shows that at one time mining occurred here and minerals were removed. Unnatural patterns on surface scanner.
Look what's happening here. These are not natural plant communities. They have been deliberately planted, cultivated, and then harvested by a higher and very complex being. These are not even natural plants. They are specialized and quite different from the other plants we saw earlier, and must have been deliberately planted, cultivated, and harvested. These plants are so specialized that they could not survive without aid of an intelligent form of life.
The regularity of these fields, the way the plants are aligned, suggests careful planning and decision-making ability. Something has been modifying large areas of the surface, a dominant being.
These specialized plants are a highly cultivated resource on this planet. How are they used?
Primarily as a food supply. But some, like the trees we saw earlier, are used for other purposes.
We've picked up an unusual formation. This is a water-bearing channel, but it's not natural. It is carrying a large quantity of water from a place of abundance. This area is normally dry. Look beside the channel. But if this water is applied to the land, which is fertile and in a temperate area, plants would grow readily.
So water, the most prevalent compound on the surface of the planet, is being used by these dominant beings, which would make it another resource.
Here is a simple machine being used to further regulate and redistribute the resource, water.
Sensors have detected the dominant beings.
Visual scanners, close on subject.
Humanoids. They resemble us very closely.
Yes, they appear to be just like our people. Astounding.
Here are more areas used to cultivate plant growth. There is a great dependence on machines in this kind of agriculture, and very few people actually working in the fields. That would suggest large concentrations of these people elsewhere, dependent on this area for food.
But I suspect that things could be different elsewhere on the planet, where growing conditions are not so favorable.
Highly probable. We see much evidence here of decision-making in the types of crops, their cultivation, the arrangement of the fields, and the relationship of this food production area to the areas where the people are concentrated. All these decisions are based on a culture, and there are likely to be many cultures on this planet, as there are on our own.
What a complex system. This must be a gathering process. Is this food intended for the people?
In an indirect manner. First, it is fed to these specialized animals, which are brought together in these regulated areas for feeding. Then the animals are used for food. What's this? A crude sort of flying machine, and it's dropping something.
Is it distributing water?
No, it is applying a chemical substance. It could be for increasing plant growth, but it might also be an attempt to control competing organisms.
What a fun-looking machine.
Here we have some more resource gathering.
Is it water they are pumping?
No. It is an oil-type substance, a liquid from deep within the planet. Analysis shows it to be a hydrocarbon derived from the remains of plants which grew very long ago.
Its use?
Primarily for energy, but it could be used in manufacturing as well. All of the machines we've seen depend on this material for their energy source. Here it is being transported. The design of the carrier shows an interest in efficiency. Large quantities are moved from one area of the planet to another.
And here is one of the carriers being unloaded. The resource must be pumped to a processing facility nearby.
This is the facility. Here, the raw resource is converted into many forms, but most are for energy. The size of the facility tells us how valuable the society considers this resource.
Here's another facility for producing energy. This one is under construction, but it has to be a device for using nuclear fuel to produce electrical energy. They do seem to be searching for alternatives.
Yes, but that fuel is a finite, non-renewable resource too. Someday they will have to find other sources of energy.
The use of energy on this part of the planet is very intense. The development of all these resources for food and other uses is based on elaborate machines which consume energy in vast quantities. Many of the resources, like water, are renewable, but this particular society seems to have developed a dependence on non-renewable resources, which could be dangerous.
Solar Terminator 2+7.
Science, can we have a review of our Phase 2 findings?
Right, Command. Basically, we have found that there is a reason for the location of everything on this planet, whether natural or people-made. They are there because of natural processes or because of decisions made by people. These people have actually invented plants and animals which they use as resources. Their agriculture is a major modification of the surface of the planet. Agriculture disrupts the natural processes.
But the conditions we observed cannot be present everywhere on the landmass. We found an area in a temperate zone with abundant water and other resources. These conditions allowed a certain kind of culture to develop.
Everything we've seen indicates that there must be high concentrations of people elsewhere, dependent on the relatively few who actually grow the food and gather the other resources.
We'll investigate those concentrations of people in the third phase of the mission. Prepare to shut down the probes. Resource and life form investigation terminated.
Program to hold position.
Sensors to standby.
Probe drive to flight idle. Visual transmissions to monitors off. Phase 2 complete.
It's a novel idea, but boy, it gets tiresome. It really does. I mean, if this was a Disney film and they were doing the same thing, there'd be some sort of like crisis or some sort of thing to wake the crowd up. But ugh, oh boy. This next film is fascinating, but it is really niche. It's I think it's made for structural engineers or mechanical engineers. It's called Loads on Structures. Enjoy.
Ever since the beginning of history, man has built himself shelters, places to live, work, and worship in. And later on, as his leisure time increased, places of entertainment. Eventually, man wanted to travel and constructed a vast transportation network. He built himself ships to travel over the oceans, roads and bridges to travel over land, and with greater technological know-how, airplanes, helicopters, and rocket ships. Structure is that part of a building, a ship, an airplane, or a machine that gives it strength and stability to withstand the forces of nature and those created by man. Like the structure of the human body, it may consist of an invisible skeleton and a covering skin, or may consist of a shell similar to the human skull. Though most structures are built for utilitarian purposes, they often must withstand large, unavoidable loads. The useful loads on structures are often not as severe as those due to other natural or man-made causes. The devastation wreaked by natural forces such as windstorms, hurricanes, floods, landslides, and earthquakes have induced man to try to better understand the behavior of structures and their load-carrying capacities in order to avoid unforeseen catastrophes. experiments are constantly being conducted to improve the safety, reliability, and strength of structures in collisions and explosions. That is, in man-made disasters. For example, an airplane crash test will help in designing future aircraft structures that will minimize loss of life and property. What are the most important loads a structure must carry, and how do they act on it? All structures must support their own weight, the so-called dead load. In addition, the structure must support superimposed loads, known as live loads in the case of buildings and bridges, or as payloads in the case of ships and airplanes. Live loads may be divided into various categories. Steadily or slowly applied loads, such as snow falling on a rooftop, furniture and occupants of buildings. Rapidly applied loads, such as hurricane winds, earthquake, and collision forces. Repeated loads, like those caused by reciprocating machinery. And finally, hidden loads. A structure may have dangerous loads on it that do not show, such as those caused by temperature changes, residual stresses, and uneven settlement of supports. This ring seems unloaded, but if cut, the ring snaps open. An inner so-called residual load was holding the two ends of the ring together before the cut was introduced. A temperature rise may also produce hidden loads. It is a frequent occurrence that roads buckle when the temperature is very high. This arch, before being heated by a lamp which simulates the heat of the sun, has the shape of the red parabola. As its temperature increases, the arch deforms, as can be seen from the deviation of the arch from the red parabola. This arch is held by brittle porcelain pins. When the arch is heated by a lamp, the internal thermal stresses may be high enough to break the supports. When external loads are applied to a structure, it deforms. You can see from this experiment that without any increase in the loads on the structure, the settlement of the foundations due to an uneven soil condition may produce distortions equivalent to those due to loads. In this post and lintel structure, the uneven settlement of the support produces total collapse. Let us examine the difference between stationary or slowly applied loads, that is, so-called static loads, and rapidly applied or so-called dynamic loads. A weight sitting on a nail will not drive it into a piece of wood, but dropped on the nail, it will. Just how effective is a dynamic load? When a beaker full of lead shot is slowly applied to a spring, the spring elongates to the center marker. when a second beakerful of lead shot is added, the spring deforms further. The elongation due to 2 beakers of lead shot is exactly twice as much as the deformation due to a single beakerful. If 1 beakerful of lead shot is applied rapidly, the spring deflects further than under the slow application of the load. If the load is actually dropped, the elongation is exactly twice as much as under the slowly applied load, indicating that in this case, a dynamic load is twice as effective as a static one. Let us investigate what is meant by slowly and rapidly applied load. When a structure is deflected, the material will try to restore it to its original shape. But in doing so, the structure swings past that position. Again, the material will try to bring back the structure, and oscillations are set up. Structures oscillate in a variety of shapes. The time required for a single full oscillation in a given shape is called a natural period of the structure. The periods of oscillation of a structure depend on its dimensions, weight, and material. For example, the period of oscillation of the spring depends on its length. A shorter spring has a shorter period. It oscillates faster. The period also depends on the weight attached to the spring. The larger the weight, the longer the period. The period of oscillation of the structure is the yardstick by which we establish whether load is slowly or rapidly applied, that is, whether it acts statically or dynamically. This spring also has a period, which is the time required to complete a full oscillation from one extreme position to the other and back again. If the load is applied over a time longer than, say, 3 natural periods, it is a slow or static load. Under such a load, the spring deflects to its static position. If it takes between, say, 1/2 and 3 periods to apply the load, the spring deflects more than under a static load. If loading takes less than 1/2 period, the load acts dynamically, and the spring deflects about twice as much as it did under a static load. When the time of application of the load is much shorter than the period of the structure, the load is called an impact load. Impact loads may have shattering effects. The loads produced by an earthquake are dynamic loads. A single earth shock may damage this building. Repeated shocks may damage it progressively and may destroy it. If a force is applied rhythmically to a heavy weight, and the force application is in step with the natural period of the structure, the deflections of the structure will become larger and larger at each load application, even though the applied force is small. In such cases, a force is said to be in resonance with the structure. Resonant loads are dangerous because of their cumulative effects. This spring, when plucked, vibrates with one of its natural periods. The unbalanced rotating motor attached to its end can apply a rhythmic force to the beam. When the motor speed is increased until it is in resonance with the natural period of the beam oscillates wildly. As the speed is increased past the resonance speed, the oscillations decrease again, since the force application is out of step with the period of the beam. A non-resonant load is evidently less dangerous than one that is in resonance with the period of motion. The various shapes into which a structure deforms while oscillating are called its modes of vibration. The first or fundamental mode is the mode with the longest period. The fundamental mode of this simple column can be excited by resonance. It presents the largest deflection at the center. By speeding up the motor, we may excite by resonance the second mode of the column. Here, the center of the column is stationary, and two other points along the beam have maximum deflections. The center is stationary, and the top and bottom halves move with large amplitudes. A complex structure exhibits a fundamental mode, the mode with the longest period. It also has higher modes with shorter periods, which you see here excited by an unbalanced motor in resonance. Notice that in a higher mode, several points in the structure are stationary. In this so-called third mode, the base of the structure, a point between the second and third floors, and a third one between the fourth floor and the roof, are stationary. Oscillations can also be excited in a structure by the motion of one of its parts. For example, if the foundation of a building are shaken by an earthquake, the building will oscillate in a combination of natural modes. Ordinarily, wind is considered to be a slowly applied load producing a static pressure on the windward side of a building and a static suction on the other. In this wind tunnel experiment, you can see the smoke lines which indicate the wind direction around the building. You will notice that the windows are pushed in at the front and sucked outward at the back. While a steady wind ordinarily produces a static pressure, when the wind blows in gusts whose period is near that of the structure, it acts as a resonance load. A steady wind acting on a flexible structure may produce rapid aerodynamic oscillations, so-called flutter, as can be seen on this flexible tent. This is a model of a suspension bridge section. Gusts blowing on it may produce violent oscillations. However, a steady wind blowing on a structure of this type may also produce rapid aerodynamic oscillations. The wind pressure pushes this plate away from the fan, but the wind pressure decreases as the plate moves away from the fan. The plate then is pulled back by its own weight, only to be pushed away again by the wind pressure, which has increased because the plate is nearer to the fan. Thus, oscillations are excited even by a steady wind. Such aerodynamic oscillations have a tendency to increase in amplitude in a manner similar to motions caused by resonance. The following scenes show how a 30-mile-per-hour steady wind, destroyed by aerodynamic oscillations, the Tacoma Narrows Bridge in Tacoma, Washington, in approximately 3 hours. We have seen that in addition to the dead load, the various live loads acting on a structure must be considered. We have seen the effects of hidden loads, the differences between static and dynamic loads, and the dangerous conditions induced by repeated loads, such as resonance and aerodynamic oscillations. All loads and their effects on structure must therefore be carefully considered.
Yeah, if I was at a rave, I would show that without the narration, or I would add like a breakbeat to the soundtrack, because that was awesome. I'd also put some echo or some delay on the narration. One last thing. This is a reel of short subjects. Enjoy. So that was some footage that I didn't know what was on it. Sometimes that happens. You have a reel that has a couple of things on it. And first was that crazy marionette. Well, it wasn't really crazy, but they were just dancing. There was no narrative, nothing, just them dancing, which I kind of love that. And then it was home movies of a vacation road trip where they ended up in Canada. There you go. Thanks for watching today. We appreciate your eyeballs and your attention. And tomorrow will be pre-recorded. In fact, probably the rest of the week will be pre-recorded because I'm going to be in Austin. And I will actually be on a plane when tomorrow's show is going on. So, and I'll try to show when I'm in Austin, I'll try to show what we're doing, where we're going, stuff like that. So, yeah. Thanks for watching. If you like what you saw, hit the thumbs up, hit the like button. You can subscribe, which also helps us out. You can watch other films that we have on our channel, and that brings us ad revenue, which we will immediately spend on storage unit rent, slowly making our way out of the storage units into our new film vault area that is climate controlled and is just better because it's at the archive. You can also donate via the Super Thanks button. Go to patreon.com/abgeeks or go to ko-fi.com/abgeeks if I didn't already say that. Anyways, I'm going to go pack. I will see you soon. Take care, everybody. Love you.